All right, so page 147, section 3.3. In 147, this is called differentiation formulas. I prefer to call this section shortcuts because that's exactly what it is. These are fast, easy ways to find the derivative as opposed to what we have been doing with using the definition. So the first thing that they tell me is that the derivative of a constant is always going to be 0. The derivative of a constant is always going to be 0. So it doesn't matter what that constant is, its derivative is 0. So if you have f of x is equal to 5, then its derivative is 0. If you have f of x is equal to pi, its derivative is 0. If you had f of x was equal to e, its derivative would be 0 because e is 2.7. That's a constant, right? If you had the derivative of 5,274,362.573, its derivative would be 0. The derivative of any constant is 0. Why? Why is that true? Well, if you notice, if we went through and we thought about the proof or the reasoning behind this, if we go back to the definition of derivative and we use that for this function, if f of x is equal to c, if I do f of x plus h, that means put x plus h in the place of x. There's not an x over here. So when I put x plus h in the place of x, it's not going to affect that function. I would still just get that constant. It's the same idea as like if you're graphing y is equal to 2. If you make an xy chart for y is equal to 2, if you put 0 in for x, you get y is 2. If you put 1 in for x, you get y is 2. If you put 367.1 in for x, you get y is 2. If you put x plus h in for x, you'd still get y is equal to 2. If you did triangle or heart in the place of x, you would still get y is equal to 2. It doesn't matter what you put in for x, y is still 2. That's exactly what's going on here when we say if we put x plus h in the place of x in that function, there is no x to replace, so I'm still just going to get that constant, whatever it might be. So f of x plus h would be my constant, minus f of x, which was just my original function, my constant, divided by h. So if I do c minus c, constant minus constant, I'd get 0. So 0 divided by h would give me 0. And the limit of any constant is that constant. So I would get the limit of 0 is 0. And so you can see that would work for any constant on the face of the earth. That would be the proof. Another way to think about this would be to think about what the graph looks like. If you graph a constant, the graph of a constant is a horizontal line, right? So if you drew a tangent line anywhere along that horizontal line, the slope of that tangent line would be 0, right? So it doesn't matter where your constant is. It doesn't matter if it's at -2 or at +2 or at +2,000. If you draw a horizontal tangent, if you draw a tangent line, it's going to be horizontal, so its slope would be 0. Slope of the tangent is derivative. So several different ways there that we can make sense of that first rule that they give us. All right, the second one that they give us is the power rule. The power rule is probably the one that we're going to use more often than anything else. And that is if you have the derivative of x to the n, you're going to take that exponent of n and move it out in front to be a coefficient that's being multiplied. And then you're going to reduce your exponent by 1. So, for instance, let's say that you had x to the 6th. I'm going to take that 6, that exponent, and I'm going to move it out in front and multiply by it as a coefficient. And then I'm going to reduce my exponent of 6 by 1. So 6 minus 1 means that my new exponent is going to be 5. So the derivative of x to the 6th would be 6x to the 5th. Okay, hang on. We have got to stop there for a second, right? Think about what it would have taken up until this point to do that derivative. X to the 6th, we would have to do the limit as h approaches 0 of f of x plus h. That means you're putting x plus h in the place of x. You're doing x plus h to the 6th, right? X plus h times x plus h, FOIL it out, get a trinomial. Multiply that trinomial times x plus h, combine like terms. Multiply that by x plus h, multiply that by... I got to to do that 6 times, right? And then combine all those crazy like terms and then go back and subtract the function and get everything to drop out and take out a common factor of h and get it to cancel and then apply the limit and, you know, 2/3 of a page and 20 minutes later I'm finally done, and now I can do that in my head in like 10 seconds. That is a happy thing, people, yes? Okay. Alright, so even if I have a constant out in front, like instead of just plain x to the 6th, if it was 2x to the 6th, still going to work the same way. I could go through and I could say, okay, let's take that exponent of 6 and move it out to the front. And then we've already got our 2x that was there. And let's take that exponent of 6 and reduce it by 1. And we would end up with 12x to the 5th. There are also lots of other types of functions that I can rewrite in such a way that I would be able to use the power rule. Okay? For instance, square root of x. How could I rewrite that so that I could use power rule? X to the 1/2. Right. So if I rewrite that as x to the 1/2, what's the coefficient going to be? 1/2 x to the, what's the exponent going to be? Negative 1/2. Exactly. So you could leave it that way, 1/2 x to the negative 1/2. Or if you wanted to, you could rewrite x to the negative 1/2, get rid of the negative by moving it back down to the bottom. And then x to the 1/2 is the same thing as square root of x. All right, look at the next one. If I have 1 over x squared, how could I rewrite that so that I could use power rule? Yes, x to the negative 2. So if I write that as x to the negative 2, now I can use power rule for it, right? So what would my coefficient be? Negative 2, and what would my exponent be? Negative 3, nice. And again, you could write that as negative 2 over positive x to the 3rd if you wanted to as well. All right, the next one that we have is f of x is equal to x. If there's no exponent, what is it? 1, right? So that's x to the 1st. So I would move the 1 out in front and have 1x, but it would be 1x to the what? What would my new exponent be? 0, right. So if I have x to the 0, that's the same thing as 1. So what we just discovered and what we just proved is that the derivative of x is always going to be 1. And that's actually another rule that they give us in the textbook. The derivative of x is going to be 1. So let's go back, because we're going to use power rule so often this year, let's go back and let's look at the derivative formula for power rule. Let's look at the proof of that. All right. If I want to prove the derivative of x to the n is equal to nx to the n minus 1, let's use our definition of derivative. So I'm going to put x plus h in the place of x in that function. So that would be x plus h to the n minus the original function x to the n divided by h. Now, if I had x plus h to the n, if I were to go through and multiply that out, like if it was x plus h to the 2nd, I would get x to the 2nd, 2xh, h to the 2nd, right? So that's what they've done here. X to the 2nd, like n is 2, 2xh, and then down here, h to the 2nd. If you think about it, if it was to the 3rd power, now you'd probably have to start thinking in terms of Pascal's triangle. But if you're doing 3rd power, that would be like x to the 3rd, 3x to the 3 minus 1, or x to the 2nd, h, plus 3x h to the 2nd plus h to the 3rd. If we had it to the 4th power, again, you definitely want to start thinking of Pascal's triangle there. So what they've done is they've just generalized a way that you could write that expanded polynomial. And then I've got minus x to the n. The cool thing is that no matter what that is, your first term and your last term would always drop out, and then every other term that you had in here would have an h in it that you could factor out and cancel top and bottom. So that then when you applied that limit as h approaches 0, other than that first term, because it just got the h factored out of it, every other term after that is still going to have an h in it. Because if you think about it, like this would be h to the 1st, h to the 2nd, h to the 3rd, h to the 4th, and so on. So every other term, when you would put that 0 in the place of h, every other term would drop out and you would only be left with that first term. nx to the n minus 1. And so you can see there the proof of why that power rule works. So in these first two, we've kind of done a formal proof by using the definition of derivative. You also sometimes can do an informal proof, and we're going to see that for the next one. So the next rule that they give us on page 149 is the constant multiple rule. And the constant multiple rule says if you take the derivative of a constant times a function, you have the right to pull that constant out in front and just do the derivative of the function. And once you're done doing the derivative of the function, then multiply by the constant. Now, that sounds familiar, right? Didn't we have like a limit law like that? Remember, if you're taking the limit of a constant times a function, you can do the limit of the function and then multiply by the constant. And isn't the derivative just a limit? So we'll see a lot of similarities with our limit laws and our derivative laws because a derivative is a limit. So let's say that we were working with f of x is equal to 3x to the fourth, okay? According to our power rule, we have the ability to say, okay, let's take that 4 and let's move it out in front so that we would have 4 times 3 or 12, and then reduce that exponent by 1, so 12x to the third. So according to the power rule, that derivative would be 12x to the third. So let's see if this constant multiple rule will give us the same thing. The constant multiple rule says that if you have a constant multiplied times a function, you can pull that constant out in front and just do the derivative of the function, and once you're done, then go back and multiply by the constant. So if we did the derivative of x to the fourth, that would be 4x to the third, and then go back and multiply it by that constant of 3, and sure enough, we get the same answer, 12x to the third, as we had gotten when we applied the power rule that we've already proven. So that's an informal proof when you take something that you've already proven and you use it to help you prove something else. So we worked this out two different ways. We worked it out with the new rule and we worked it out with a rule that we've already proven. And since we've gotten the same answer, then that's an informal way of showing that our new rule works as well. All right, look at the next one. For the next one, it's actually two rules that I've written as one. Over on page 150, they give us a sum rule and a difference rule. And here's basically what it says. If you're finding the derivative of the sum of two things, you can break that apart into two separate derivatives. So you could take the derivative of just the first thing and the derivative of just the second thing and then go back and add those derivatives. The difference rule says the same thing. If you're taking the derivative of two things that are being subtracted, you can break that into two separate derivatives, find those two derivatives separately, and then just go back and subtract their answers. So that takes me to our next example. I have a lineup of things here that are being added and subtracted. So according to the difference and the sum rule, I have the right to go through and do the derivative of each of these pieces individually instead of having to do the derivative of the whole thing all at once. And then I can go back and just add and subtract those derivatives. All right? So let's start with x to the 8th. What would the derivative of x to the 8th be? 8x to the 7th. And what would the derivative of 12x to the 5th be? 60x to the 4th. So I found the two derivatives separately, and according to the sum rule, then I can go back and say, okay, since those two are being added, I'll just add the two derivatives. All right? Same idea for the next piece. The next piece, I have minus 4x to the 4th. What would the derivative of 4x to the 4th be? 16x to the 3rd, right? So we've said, okay, if I had these two derivatives and they were being subtracted, I can find the two pieces separately, find their derivatives individually, and then just go back and subtract their answers. So let's keep going with that same idea. What's the derivative of 10x to the 3rd? 30x squared. The derivative of 6x? 6, and then we would subtract. So two ways that you could think of that. You could think of this as 6x to the 6x to the 1. So you would say 1 times 6 is 6, and then x to the 0 would just be 1. Or you could use your constant multiple rule that says if you have the derivative of a constant times a number, then pull the constant out in front and just take the derivative of your x. So if you take the derivative of x and you know that's 1, then go back and multiply it by your constant of 6. That also would give you 6. And again, it was being subtracted, so then we can put our subtraction sign in. And what's the derivative of 5? 0, because the derivative of a constant is a constant. and I'm done. You do realize that that problem would have taken me like a full 8.5 by 11 sheet of paper and 20 minutes, and the likelihood of me dropping a sign somewhere in the middle of the thing and getting the whole thing wrong after I've done that is, for me anyway, is high. And now I can do that whole thing with no work in my head, and once I've done this for a little bit, I could probably do that in about 20 seconds time instead of 20 minutes. That is a happy thing, yes? Man. All right, example 4, over on page 151 says, find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. So for that equation, tell me where you're going to have a horizontal tangent line. Any ideas, suggestions? Where do I start? Where would I have a horizontal tangent line? What? If it was a parabola, yes, it would be at the vertex. So if we're thinking of maybe like a cubic, it's going to be like at a maximum or at a minimum, right? We don't really call that a vertex, but it's that same kind of idea. So we're thinking about like if it were something like this, at the maximum or at the minimum is where I could find horizontal tangent lines. How do I solve that algebraically? How do I find that? Because up until this point, I've needed a calculator for that, right? To find like a maximum or minimum, I had to hit the max or min button on my calculator. So how could I do that? What's remarkable about a tangent line with what we studied? Its slope of the tangent line is the derivative, right? Which in effect is a limit. And the slope is what? Why is the slope 0? Because it's a horizontal line. So if I want to find anywhere on this graph that I could draw a tangent line and it be perfectly horizontal, I'm looking for where the slope is 0. And slope of the tangent line is what? Derivative. So where am I looking for what the derivative is equal to? 0. Yeah. So if I want to find a horizontal tangent line, all I need to do is figure out where my derivative is equal to 0. All right, so let's take the derivative of this guy. What would the derivative of x to the 4th be? 4x cubed. And then the derivative of 6x squared? 12x. And then we're going to subtract that. And the derivative of 4 is 0. So there's my derivative. And if I want to find horizontal tangent lines, I'm going to set that derivative equal to 0. All right, so if I'm going to solve that, take out greatest common factor and set each piece equal to 0. And so I find out that at 0, positive square root of 3 and negative square root of 3 is where I would have horizontal tangent lines. So if you throw x to the 4th minus 6x squared plus 4 into your calculator, you actually get a graph that looks something like this. It's there in your textbook as well. Not perfect, just rough sketch there. And so sure enough, when I draw tangent lines, this one actually is higher up, like up here somewhere. But when I draw tangent lines, it's here, here, and here. And that just so happens to be at negative square root of 3, 0, and positive square root of 3. So not only did I just find out where I have horizontal tangent lines, I just found a way of finding maximums and minimums on graphs. And until this second, I did not have a way to do that without my calculator. Because the only way that we knew how to find a maximum or a minimum was to use our calculator. And that's where they're going to go with this eventually. So that's a really cool thing too. All right, look at the next one. The next one they give me is called the product rule. And the product rule says that if you have two things that are being multiplied, thus product, right? If you have two things that are being multiplied, my product rule says take your first function and multiply it by the derivative of your second one, and then add your second function multiplied by the derivative of your first one. So the way that we'll say that typically is we'll say first times derivative of second plus second times derivative of first. Now, something that bothers me a little bit about our textbook is that this is the rule, this is the way that it's typically stated, this is the way they state it in the textbook. However, you and I both know that you can add in any order, so you could interchange these, like you could put this one over here and you could put this one over here. You also can multiply in any order, so you technically could reverse the order of these two. Every single time I do one of these problems, I am always going to do it in this exact order right here so that it's not confusing to you. However, in our textbook, occasionally they'll reverse the order of these two, or they'll reverse the order of these. So don't let that bother you if you see them do that. All right, so here's another one of those informal proofs. They give me something, 2x to the third times 4x to the fifth, that I could multiply and simplify. So 2 times 4 is 8, x to the third times x to the fifth is x to the eighth, and then take the derivative of that simplified version. So what's the derivative of 8x to the eighth? Yes, 64x to the seventh. What they want me to see is that if instead I use this new product rule that they just gave me, and I worked this out by doing first times derivative of second plus second times derivative of first, I would get that exact same answer, and in that way we are informally proving that formula. All right, so let's try it. If we go through and we do first, that was the first function, 2x to the third, times derivative of the second. What's the derivative of 4x to the fifth? Plus second, so the original second function was 4x to the fifth, times derivative of the first. What's the derivative of 2x to the third? 6x squared. So regular first times derivative of second plus regular second times derivative of first. All right, so if we do some simplifying over here, 2 times 20 gives us 40, x to the third times x to the fourth, x to the seventh. Right, when your bases are the same and you're multiplying, add your exponents. All right, then here 6 times 4 is 24, x to the fifth times x to the second is x to the seventh. And then I have like terms, right? Because x to the seventh and x to the seventh, I can combine my coefficients, and I just so happen to get 64x to the seventh, the exact same answer here that I got here. So again, an informal proof because they've used power rule to show that we would get the same answer as when we use product rule. Now, there's another very important lesson that I want to get from this example. A lot of times there is a fast way to do these problems and there is a slow, longer, harder, more involved way to do these problems. Any time you can simplify your function first before you take your derivative, you will make your life so much easier. You can see I'm going to get the same answer either way, but because I simplified over here first, it was a whole lot easier to take the derivative. So anytime they give you a product, check to see if maybe you could just like FOIL it or something like that first, because then you'll typically be able to use power rule. Okay, so watch for that because you'll make your life a lot simpler. The next one they give me is the quotient rule. Quotient is the answer to a division problem, and that's the case here. If you have one function being divided by another, you're going to do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And again, we've written it out in words over here since that's typically the way that we say it. So I have this guy right here. I have a quotient. Here's another one of those. Let's say this 6 wasn't here, so I'm going to stick the little laser pointer over the 6 to kind of cover it up. Let's say that the 6 was not there. I would not work this problem with the quotient rule. I would simplify it first because I could go through and say x to the second divided by x to the third, and that would be x to the negative 1, right? X divided by x to the third is x to the negative 2. Negative 2 divided by x to the third is negative 2x to the negative 3. Then I can use power rule on that, right? So again, if there's a way that you can simplify it first And on these quotients, those are the ones that are typically the biggest difference. If you just have a single term in your denominator where you could go through and simplify that and get rid of your quotient so you don't have to use quotient rule, you can typically go back to using power rule, and that's so much easier. So look to see if you can simplify what you're taking the derivative of before you take the derivative. In this case, there's no way to simplify this. I can't go through, I could, go through and write x squared over x cubed plus 6 and x over x cubed plus 6 and negative 2 over x cubed plus 6, but that would make it worse instead of better. That doesn't reduce down in any way, so I'm going to leave it as it is, and I'm going to use my quotient rule. So I'm going to say denominator, so just the regular denominator, times the derivative of the numerator. So what's the derivative of x squared plus x minus 2? 2x plus 1. Minus the original numerator, unchanged, times the derivative of the denominator. So what's the denominator of x cubed plus 6? 3x squared. All over our denominator squared. Now we have joyful simplification, right? So I'm going to go through and I'm going to FOIL these first two binomials here. So x to the third times 2x is 2x to the fourth. X to the third times 1 is x cubed. 6 times 2x is 12x. And 6 times 1 is 6. And then I'm going to distribute the 3x squared to this trinomial. So we could go through and say 3x squared times x squared is 3x to the fourth. 3x squared times x is 3x cubed. 3x squared times negative 2, negative 6x squared. So now if I combine like terms, I've got 2x to the fourth minus 3x to the fourth, so that's a negative 1x to the fourth. X to the third minus 3x to the third is a negative 2x to the third. I didn't have any square terms up here, but I do have minus a negative 6x squared, so that'd be plus 6x squared, and then plus my 12x plus 6, all over x to the third plus 6 squared. And that is my answer. I do not need to FOIL out that denominator. Really, it's better for me to leave it in factored form, because if there was any way to factor my numerator, I would want to go through and factor my numerator and see if I had any common factors in the numerator and denominator that would cancel out to enable me to simplify this down. Now let me give you a suggestion for both our test and the AP exam. We spend what feels like half of our life trying to simplify our answer to match the one that's in the back of the book. So in the back of the book, they might FOIL this out, or in the back of the book, they might find a way to cancel this or take out a common factor or something else. So just because your answer is different from the one in the back of the book doesn't mean yours is wrong, but you do need to go through and try and find a way to match yours with what's in the back of the book to see if you can get to what's in the back of the book. Because that is fantastic preparation for the AP exam for the multiple choice section. On the multiple choice section, they're going to ask me to take a derivative like this, and I'm going to have 4 or 5 answer choices sitting there, and I got to find a way to make the answer I come up with match one of those answer choices. So that practice simplifying that we do to match the answer that's in the back of the book is great preparation for the AP exam. However, on the FRQs, you do not have to simplify. If they ask you to take the derivative and you left it exactly like this, you would get full credit. There are some cases that they do require us to simplify, and when we get closer to the AP exam, we'll talk about when you do and when you don't. You don't want to waste time simplifying if you don't have to. So when it comes to our tests, to try to help you prepare for the AP exam and try to help you learn how to budget your time for the AP exam, if you're looking at a problem like this, and let's say this problem was worth 8 points, 6 points are sitting right here. And then it's just a point or two in terms of simplifying it down. So I would suggest that when it comes to your test, you go through and you do all of your derivatives first, and then go back and simplify as you have time. So you'd want to go back and you'd want to do the derivative first, wait for the simplification. Do the derivative first, wait for the simplification. Once you get all your derivatives done, so you know you've got the bulk of all your points, then go back and pick up the extra point or two on each of them by doing the simplification. And you would want to approach the AP exam that same way. Okay? So as we're focusing on the AP prep at the end of the year, we'll be talking about, hey, here's where you're going to pick up most of your points. You can pick up an extra point or two here, but don't waste 5 minutes trying to pick up a point and then not get to 5 other points, either on your test or on your AP exam. All right, example 10. Example 10, they ask us to create the equation of the line that goes through the point 1, 1/2, and is tangent to the graph y is equal to square root of x over 1 plus x squared at that point. So find an equation of the tangent line to the curve at that point. I have a point. What do I need? A slope. Yes. So how do I find slope? Derivative. So we're going to go through. Again, I would want to see, is there any way to simplify this before I start doing a quotient? If that 1 were not there, if I were just looking at square root of x over x squared, I could say square root of x is x to the 1/2. So x to the 1/2 divided by x to the second, I could simplify that, okay? But however, in this case, I can't simplify, so I'm going to have to use my quotient rule. So I'm going to do denominator times derivative of numerator. We have actually already done that derivative today. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. Minus numerator times derivative of denominator. What would the derivative of the denominator be? 2x. All over the denominator squared. If I am asked to find a derivative at a value, do not waste your time simplifying this thing, distributing, foiling, combining like terms with x's, if you can put the number in the place of all of the x's, right? Oh my goodness, is that easier? So let's go back, since I'm trying to find the derivative when x is equal to 1, let's go back and just put 1 in for x, 1 in for x, 1 in for x, 1 in for x, 1 in for x. And my life just got a whole lot easier. So if we go back and plug in, 1 squared is 1 plus 1 is 2. And then over here, 1/2 of 1 is 1/2. So 2 times 1/2 is 1. Then here, square root of 1 is 1 times 2 is 2. And then down here, 1 plus 1 squared is 2. Squared is 4. There's my negative 1/4 and I'm done. That was a whole lot easier than having to work with all those x's. So now I have a point and a slope, and I could use point slope form, or I could put it in slope intercept form or standard form or whatever they ask me for. Okay. All right. So here is our homework for tonight. And again, just a strong reminder, several of the homework problems are easier if you simplify them before you take the derivative, just like we did up here, where we found the product and then we're able to use power rule as opposed to using product rule. Or actually simplify to find the quotient first, and then you can use power rule instead of using quotient rule. Okay?